Hello everybody and welcome back. Let's talk about today's LeetCode problem, stream of characters. I'm going to explain the tree solution in detail along with the intuitions of how I actually thought about it and then how to actually implement that in Python 3. Let's get started with the problem discussion. Alright, let's try to understand the example, the test case given to us in the problem statement. We have three different words like CD, F, KL and a stream of characters like A, B, C, D, blah, blah, blah. What do we do next? As they mentioned, we have to look at the stream of characters that forms a word called the stream word. So we'll have to actually create the stream word ourselves. And we'll see that the stream words is going to be A, then AB, then ABC, then ABCD. What I'm trying to do here, I'm just looking at this character, say D, and I'm looking at the previous stream word and I'm appending this character to it. As simple as that. So this is a stream of characters that is coming. And every time I look at a character, I'm going to add it to the stream word. I'm going to take that character, add it to the end, and keep on doing that until the stream of characters ends. All right, so we have the stream of words right now with us. What next? So our goal was to return true or false if the stream word had a suffix inside of words. So let's go ahead and actually enumerate all of the suffixes inside each of these stream words. I'm not looking at the stream anymore, I'm looking at the stream words. And I want to know what all are the suffixes inside of this word. All right, let's go ahead and do that. So this is all we have. So for the word A, I have the suffix as A, pretty simple. For the word AB, I have two suffixes. First is the B and second is AB, right? Suffix means that I'm going from the behind to the front. So I'm going to look at the B character first and then AB. Similarly, when we have the characters ABC inside of the word ABC, we'll have C, then BC, and then ABC. Similarly for D, CD, BCD, and ABCD. Again, very simple, nothing special. We're just going in the reverse direction, creating these suffixes words. But there's something interesting happening inside of this case. And I want you to try and figure out that before I tell you the answer. Cool. Let me tell you the answer now. In this word, we have the suffix CD with us. And this suffix CD is present inside of this words as CD over here. Which means that for the character D, these yellow states are, by the way, just intermediate states. D is the real input given to us and the inputs are in black. And for the input D, when we accept the character D from the input, we're going to have CD as one of the intermediate states in the suffixes. And this CD is present inside of this words over here, which means that we can return true for this case. And if you look for the characters, for the words A, B, AB, B, BC, C, ABC, whatever, all of these words, if you look at all of them, none of them match with any word inside of the words. Right? So that is the reason for having false over here. And just by using this stream of logic, we can just keep on doing this again and again. And first thing we'll do is look at the character. We'll append this character at the end of the previous word, enumerate all the suffixes, and then finally trail if one of these suffixes matches with a word. Even in saying this, I can feel the inefficiency coming through. So we want to actually start to think about a proper solution now. How can we do that? Well, let's talk about the intuitions behind the solution approach. All right, let's actually talk about the observations and logic needed to solve this problem. And the first thing we're going to do is talk about what the problem gives us and if there is something we can extract out from it. What are the intuitions behind getting to a solution? The first thing I want to tell you is that the word suffix was interesting. And that's because when I looked at the question for the first time, I got thrown off by the suffix. It was only later that I realized that the suffix of a word is just the same as the prefix of the word reversed. So I can take a word, I can get all of the suffixes of it, and then I can also reverse the word, get all of the prefixes, and they look pretty much the same. Let me show you with an example. Let's say we have the word cat with us. For the word cat, what are the suffixes going to be? Well, we can start off with T. So that's one suffix. Then we can have AT. Remember, we're going in the reverse direction. So that is important to know. Then we have AT and then we have CAT. Pretty simple. All right. What about the word when it gets reversed. So when we reverse the word, what do we have? CAT becomes TSC. Pretty simple. Now let's get all of their prefixes. Now the prefixes of TSC is going to be T, then TA, and then TAC. Pretty simple, nothing too special, right? We've just enumerated the suffixes and the prefixes. But what do you notice in between those two? If you look at the word cat, and this is the word tack, right? It's just reversed now. This is TA, this is AT, this is T, this is T. So there is a lot of similarity between both of them, although they aren't exactly the same. By the way, this can also be an issue that you can face while implementing. So be careful of this reversing thing that's going on. So it's not exactly AT over here, it's TA. It's one time also reversed, but pretty much both of these are looking the same. And this is something we can use, yeah? So what I'm going to do is, I'm going to ask the question now. We have a lot of words. We have like 2000 words with us. Is there a way we can store all of these words? Now I can think in terms of prefixes and not suffixes. Suffixes was confusing a bit. So we just thought in terms of prefixes by reversing the word. Now, is there a way we have an efficient way of storing all of the words, given that we already know the information of we're dealing with prefixes? What we're asking is that, is there an efficient data structure to store all of the words? And there is one. There is a data structure called a trie or a prefix tree. I've already explained that in a solution. You can look at the info card up over here. And I've explained the intuitions and the logic and the observations needed to actually code the tree solution up. It's a pretty good solution, and it's going to form the basis of this solution. So I'll highly recommend you go and watch that first. Believe it or not, just by these intuitions, just by understanding that there's a data structure called trie which can store all of these efficiently, we already have a good starting point. And believe it or not, the rest of the solution is just implementing the trie and the surrounding logic with it. So let's get started with the coding. For the sake of my time and yours, I'm not going to implement and write down the entire tree data structure from scratch. However, I have written it down already over here, and I can walk you through what's happening. Since we want to implement this data structure, we want to implement a single node inside of this data structure. So what is it going to look like? We have three key pieces of information. What is the current character we are looking at? What is the child, or what are the children of this particular character? And the third, which is the most important one and which some people can miss very easily, is the self.end one. And this basically says that whether, and this end is a boolean, saying that whether this particular node, this particular character marks the end of a word or not. Very simple, but very important. All right, then we have the trie data structure with us. So we have self.root as a dummy node. Mostly for implementation reasons, I've explained that in the video solution I linked. And then we have a function called addWord, which is going to take the input as a word, iterate over all the characters in the word, and add them in the trie one by one. All right. Now we can actually think about the stream checker function. And the first thing I'm going to do is have this trie data structure with me. And what was the entire point of this data structure? What was the entire point of trie? We wanted an efficient way to store these words. So let's go ahead and add the words. We'll do self.trie.add word of word for word in words. This is fine. But also we realize something. The entire question is talking in terms of the suffixes, but we realize that what we have implemented is a prefix trie or a prefix tree. So we'll actually have to reverse this word to be correct. We have just flipped all of these words. We've reversed all of these words so that now we can insert them into the data structure. Again, very simple, something we've already discussed. Now, when it comes to the query, what's happening? Each of these queries is going to look like a stream of characters. So we have A, B, C, D, blah, blah, blah. And what's happening in those cases? Well, when we have the character D, we'll just look at the previous stream word and add the character D to the end of it. So we'll have ABC plus D, which gives us ABCD, and so on and so forth. So we'll actually go ahead and create a self.word, which is going to be the stream word. And every time we see a character, I'm going to add it to the word. Simple. All right, now what? Why did we form the stream words in the first place? It was so that we could iterate over the suffixes of this word. So we're going to look at the self.words suffixes. Right? I want to get all the suffixes of this word and say if one of these matches a word inside of the trie. Now we already have trie to work with. And what I can do is write a function over here and I can say does exist, which can tell me, and the entire point of this function is to tell me whether a particular word given as the input exists in the trie or not. Because we've already added a bunch of words and we can detect suffixes this way, right? We can just write a does exist function, which tells us whether this word exists in the data structure or not. As simple as that. How can we do that, by the way? Well, the first thing we want to do is have a current pointer, which is going to be self.root. Right, we're going to start at the root of the tree. And then what? For every character inside of the word given to us, I want to make sure that I go to the next character. So I'm starting at the current character, which is the root node, and then I want to move to the next character, and then to the next, and then to the next, and so on and so forth. How can I move to this next character? We know from the data structure and from the node structure that for every single node, we have a character C, and we also have the self.child information. So I can just look at the current.child. So current is a node, and I want to look at its node's children, all of the list of all of the children. And from this children, I want to know if there is a character C present inside of it or not. Because if there is a character C present, I can move to that character. And then I can again look at all of its children. And if I find a character match, I can move to that. And so on and so forth. I can keep on going. But there's a catch. I can do this, that's fine, but only if C is present inside of this current.child. Because if the C is not present, what does that mean? I wanted to know whether this word, a suffix of this word existed inside of the data structure or not. And here I have a condition. If C not inside of this current.child, what happens? We have a break, right? From a list of children, we found no character that matched, which means that we don't really have anywhere to go. We have to break away. And what does breaking away mean in this case? It means that we have not found a suffix successfully, and we can just return false right away. All right, cool. There's one more thing now. As we are moving over these characters, what do we want to keep on checking? What's the point of doing all of this? The point of doing this and writing this function is that I want to ask the question, is there a suffix of word that exists inside of this data structure? And how can I detect that? I want a way to somehow figure that, you know what, there is a word that we added early on. There's a word that we added early on that ends at this particular character. Is there a way we can know if a particular word ends over here? Yes, we can do that. So we can just say, you know what, if current.end is true, if there is a word inside of this words list, that has an ending character at this point of time, which means that we have successfully found a suffix. And so I can return true right away. And if not, well, let's just return false. I don't think we'll ever reach this case, but sure, we'll write that. All right, so now I have the does exist function and I can simply write it like this. And I can return self.trie.doesExist of cell.word. There's a small catch over here, by the way. I'm going to run the code and show you it's wrong. Right, it's wrong. Why is that wrong? All of them show false, 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 false. The logic we discussed said that it would work. What's happening? Let me show you one more thing. Remember how when we looked at the cat example, we had cat and tac, and we observed that the suffix and the prefixes are very similar in the characters. So we have TA, we have AT, then we have CAT, we have TSE, but all of these are reversed. So what we have to do also is consider the suffixes and the prefixes in the reverse direction. We have to consider this word also in the reverse direction. So we're going to flip this word around and then run this code and get it accepted. So I'm going to show you. Let me submit this. Hopefully this works out. Cool. So we get a runtime of 2156 milliseconds. Pretty bad, but it works. So I'm not complaining. Alright, anyways, this is it for the solution to the problem stream of characters. I hope you liked this video, and if you did, give it a thumbs up. If you want more of these detailed high quality video solutions, subscribe. And as always, thank you so much for watching.